So let's get on with it. Car battery. I told you to develop the equations for the half reactions. This is what's happening at the anode. This is what's happening at the cathode. Since, as written, the anode reaction liberates 2 moles of electricity, the cathode reaction consumes 2 moles of electricity, we're ready to add them up. Don't need any coefficient adjustment. If you look at the electrochemical potentials for each of these half cells, these are not contained in our table, but you can find them online, whatever have you. This one, I believe, that one, is, let me look at this. Where did I write these potentials? Yeah. This one is plus 0.36 volts, of course measured relative to the standard hydrogen electrode. This one, as written, is plus 1.68 volts, measured relative to the standard hydrogen electrode. Now, of course, in a table, this would be written in the opposite direction, and you'd see it as minus 1.68 volts. But this is the one which has been reversed in the coupling process. So, if you add up these E0 values, you see you get about 2 volts. Does that keep with the fact that your car battery is made out of 6 of these cells connected in series? That gives you the 12 volts operating potential. Now, when you add these halves, here's what you get for the net cell reaction. Now, at this point, I direct your attention to the information you see at the top of page 2218, which I hope you've read. Keep in mind, for an electrochemical cell, a functioning electrochemical cell, one which delivers usable electrical energy, for this cell to operate properly, the oxidation part of the reaction must be physically separated from the reduction part. Back to start. When we recognized that zinc is a stronger reducer than copper, we did so by putting zinc in contact with the conjugate oxidizer of copper, which is hydrated copper ion. And we put copper in contact with the conjugate oxidizer of zinc, which is hydrated zinc ion. What did we observe? Zinc immediately reduces copper ion, converting copper ion to copper as zinc is oxidized to hydrated zinc ion, and copper does nothing to zinc ion. So that tells us that zinc is a stronger reducer than copper, and hydrated copper ion is a stronger oxidizer than hydrated zinc ion. But with the zinc standing in direct contact with hydrated copper ion, we have a short circuit. Are electrons flowing in that system? Absolutely. Directly from zinc atoms to hydrated copper ions. But if you want to use these electrons, you've got to force them to travel through an external circuit into which you can fix a light bulb socket or whatever you want to power up. We did it with a voltmeter. So here's the car battery. We recognize in each half reaction hydrogen sulfate ion, and in each half reaction hydronium ions. To these hydronium ions and hydrogen sulfate ions for the operation of the car battery, the hydronium ions, which are part of the cathode reaction, have to be physically separated from the hydronium ions, which are part of the anode half reaction. Same question applies to the hydrogen sulfate ions. If we don't separate these, will we have a short circuit and the car battery won't work? The answer is no, the car battery will work just fine. Take a look further at the components of the system. Here's the reducer. Lead solid. Is it in solution? No. It's a solid, right? Here's the oxidation product, lead sulfate. Is that in solution? No. Here's the oxidizer, lead dioxide. Not in solution. Here's the reduction product. Solid, not in solution. So if you look at a diagram of your lead storage battery, which you can see in any textbook, which you can see online, you'll see we don't have to separate the chemical components of the anode reaction from those of the cathode reaction, because the reducer and the oxidizer are not in contact with each other. They're each distinctly different solids. So the consideration that's put to you in question 2218 doesn't apply to the operation of this electrochemical cell. So are these cancelable? The answer is yeah. I can call this 2 and call this 0, and I don't have to separate the two hydrogen sulfate ions. I can keep them together. But keep in mind, in a few moments we're going to look at an electrochemical system which, if we wanted to serve as a source of usable electrical energy, you won't be able to do this. How will you recognize when this consideration applies? Are the reducer and oxidizer solution species? Or is one of them a solution species? If so, they got to be separated. Like zinc with copper ion. Because the copper ion is a solution species. All right. Now with this, when I wrote this information at the top of page 2218 on writing net cell reactions for voltaic cells, I wrote a net cell reaction. Take a look at the net cell reaction you see on page 2218. And see if in considering this issue your instructor failed, flunked, lost 100,000 points. You see the net cell reaction on page 2218? What's the oxidizer? What's the reducer? Are you looking at the reaction? What's the oxidizer? Iron. Iron is not the oxidizer. Iron is a nail. Are you looking at the reaction equation on 2218? I want to be sure we're talking about the same thing here. What is the oxidizer? It's this hydrated iron hydroxide. That's the oxidizer. This is a form of iron rust. And the reduction product is what? Iron. What's the reducer? Zinc. What's the oxidation product? Zinc hydroxide. Hey, are these in solution? Are they in solution? No. They're not going to be in physical contact with each other in this system. So I flunked. I wrote this keeping in mind what I have so far shared with you, or having in mind what I've so far shared with you, and forgot. Hey, these things aren't going to be in contact with each other. And how did I learn this? I learned this when I myself looked up on the web an operational diagram for the lead car battery. And I said, what the hell's going on here? How come these hydronium ions are not separated from each other? And then it occurred to me what's going on here. These are the kind of things which textbooks have a habit of not telling you. And I have a feeling that they don't tell you because they don't know. I learned this the hard way, but at least I learned it. So, for the example reaction on 2218, are the hydroxide ions, which you see as reactants and products for this reaction, are they cancelable? Yes. You're damn right they are. So I made a goof. 2217, you can answer these. They all follow from the stuff we did in the redox demo, plus question 2215. Like, how do we know that sodium is a stronger reducer than zinc? Hey, sodium murders water. Zinc does nothing in water. What else do you need? How do we know that zinc is a stronger reducer than copper? Well, we know that at least two ways, don't we? Zinc clobbers copper ion. Copper does nothing to zinc ion. Zinc is oxidized by 1 molar hydronium ion. 1 molar hydronium ion does nothing to copper. That kind of stuff. And so we go to electrochemical arithmetic. Two parts. Faraday's law and the Nernst equation. Faraday's law is the quantitative consideration we must make, which is in regard to the amount of usable electrical energy or the operating current that's deliverable by an electrochemical cell, or for electrolysis processes. Like, what kind of voltage do we need to apply? Or how much current do we need to pass? If we want to take zinc plus copper ion, make zinc ion plus copper, and run that in reverse. That's what Faraday's law is about. Faraday's law distills into this quantitative relationship. M is mass of material. Like, for example, by this reaction, with a given current flowing for a given amount of time, how much copper metal can we make from a solution containing copper ion? The components of the equation. This Q is charge. I really don't know why chemists have used the symbol capital Q for this, because it's just like reaction quotient. So you got to use kind of a different script for these Q's. So I wrote over there, well, not yet. When we look at the Nernst equation, that's got Q in it, but that's reaction quotient. More commonly, Q is written this way, but in 2045 you learn that small q also means heat. So you've got a symbol problem here. I don't know, I'll change this to something else in the future. But then my book will be different than every other damn book, and they'll look at Horvath's book and say, what the hell does this mean? Things you run into in science. In this case, Q is charge in coulombs. Coulombs is amps times seconds. Current? Well, times time, but time is usually expressed in seconds. So amps is coulombs per second. That's charge. Current. Squiggly M is formula mass. You've seen this symbology before. F is the Faraday. The Faraday is simply the total electric charge, 96,500 coulombs, borne by a mole of electrons, and Avogadro's number of electrons. And N is moles of charge transferred. To get N, you have to look at the reaction which is under consideration. Example? If I want to turn hydrated copper ion into copper, given that in hydrated copper ion the oxidation state of copper is +2 per mole of copper I wish to make, I have to pass 2 moles of electricity. 2. That's N for this half reaction. Now, one general remark. To use Faraday's law successfully, which is on the information sheet, Again, I don't expect you to derive this. You can, but it's not necessary. I don't expect you to memorize it. You can, but I don't hold you responsible for that. What I want you to do is to know how to use it. And the real way to know how to use this is by what? Consideration. It's called dimensional analysis. Let the units talk to you, and then it will work quite straightforwardly. Question 2218 is about the zinc battery that's discussed in the same part of the text, same part of the notes. You're told about a battery which operates on the oxidation of zinc, and the battery is constructed from 2.5 grams of zinc. So question 2218 says, if I wanted to make this battery from aluminum rather than zinc, how many moles of aluminum would I have to use? Well, what this is really asking you is, in my 2.5 grams of zinc, which is what the battery discussed in the notes was made from, how many moles of zinc is that? And then, after determining moles of zinc, if I wish instead to make the battery from aluminum, will I need more moles of aluminum, fewer moles of aluminum, or same moles of aluminum? More moles, fewer moles, or same moles as moles of zinc? More, fewer, same?
Fewer.
I heard a vote for fewer. Any seconds to that? I'll second that. Why can I legitimately second that? Wait a minute. Aluminum atoms are neutral. They don't have positive charge density. Zinc. What's the only positive oxidation state shown by zinc in its chemistry? This I expect you to know. +2. What's the only positive oxidation state shown by aluminum in its chemistry? +3, and therein lies the difference. As a mole of zinc is oxidized, 2 moles of electricity are liberated. Whereas as a mole of aluminum is oxidized, 3 moles of electricity liberated. Right? So I don't need as many moles of aluminum to give me the same amount of moles of electricity. That's what this question is about. So based on unit analysis, given that my understanding of the question tells me I want to relate moles of aluminum to moles of zinc, I start with this as my first factor. Because immediately I've written 1 mole of aluminum. This says get moles of aluminum. And textbooks are notoriously backwards about this process. They don't do dimensional analysis worth a damn. That's terrible. But if I am going to write a setup and apply dimensional analysis correctly, the first factor I'm going to write is always going to identify or in some way refer to the unit or units which this question requires me to get. Then I got to be on the right track. And if I do anything else, then I'm not paying attention to what dimensional analysis is all about. Now, as we've just recognized, per mole of aluminum I can get 3 moles of electricity. Well, unit analysis now tells me I got to get moles of electricity to go away from the denominator of this first factor. So I'll write 2 moles of electricity per moles of zinc, because I want a relationship between moles of aluminum and moles of zinc, and this gives it to me. But the quantity of zinc described in the cell, in the battery described in the notes, is referred to 2.5 grams of zinc. Now I can straight away just convert this with the first calculation to get moles of zinc, but this will do it all in one step. 2 moles of electrons per moles of zinc, and whenever I want a relationship for any material, which is involving moles of the stuff to mass of the stuff, or mass of the stuff to moles of the stuff, what am I asked to pay attention to? Mass to mole or mole to mass for any stuff. Molar mass. Formula mass. So you get out your periodic table as necessary and determine formula mass. This we can't do with this table. Doesn't have any mass information on it. But the table you have in the notes does. And then it tells me this battery is made from 2.5 grams of zinc. So with all the considerations before us, we've established a relationship, a setup here, which pays attention to all these considerations and gives me moles of aluminum relative to the 2.5 grams of zinc straight away. 2219 is talking about the electrolysis of a molten metal chloride. The general formula for the metal chloride is MCl3. Well, if I recognize in MCl3 that chloride ions have an oxidation state of how much? -1. Whatever this metal is, has got to be in an oxidation state of +3. So I know this is the chemistry which is going on. Which means, if I want to find out what this metal is, and I'm told that by this electrolysis process, I made 2.695 grams of the metal, and I want to identify the metal. What property of this metal do you think we want to calculate? Molar mass. And get out the periodic table and see what the heck metal this is. So I'm already letting dimensional analysis tell me that I've got to have a relationship between mass of the metal and moles of the metal. So I'm writing this down first. Because now I got mass of the metal in the numerator, don't I? What should I write next? So that I will get a reference to moles of the metal in the denominator of the setup I'm trying to develop. Now you can work this stuff by just shoving data into this thing. But if you want to understand it, you have to do what we're presently doing. You see this? What's this tell us? 3 moles of electrons per
1 mole
of the metal, right? And there I have it. Mass per mole. So now I just carry on with my dimensional analysis, recognizing that along the line, as I continue to construct this setup, moles of electricity have got to go away. Well, what information do I have in a use of Faraday's law which will allow me, unit-wise, to eliminate moles of electrons? Faraday constant. So, all right, 96,500 amps times seconds. That again is the Coulomb per mole of electron. And there goes moles of electrons. And I'm told that to make this 2.695 sample of metal, I did this with what kind of current, magnitude-wise? 10 amps. Am I going to multiply by this current or divide by this current? If I multiply, I get amps squared. What the hell does that mean? Doesn't mean anything, does it? So there goes amps. And I was also told that this electrolysis was carried on for how long? 25 minutes. Well, I think you know how to relate minutes to seconds to hours, whatever have you. So I have to divide by time, don't I? Because up here I got seconds. So I'm going to write times 1 over t. You can put in that part. And I'm going to get 52.0 grams metal per mole of metal. What do you think the metal is? Look at the periodic table you got in the notes. What is it? Chromium. Done. Question 2220. The same as 2218. No more, no less. In question 2218, we established a relationship between zinc and aluminum on the basis that the oxidation of zinc gives 2 moles of electricity, whereas the oxidation of aluminum gives 3 moles of electricity. In 2220, you want the same kind of relationship established between magnesium and chromium. In this case, with chromium in the +3 oxidation state. Same thing. Pardon me, 2218. So we go to Nernst. Nernst is derived in the notes. From what is the Nernst derived? Did you look at this? That's what Nernst is derived from. The derivation's in the notes. I don't care about the derivation. What I care about is your ability to use the Nernst equation successfully. So the Nernst equation, like these other relationships, are on the information sheet. In its most familiar form, here's the Nernst equation. You put together a number of constants to get 0.059 V volts divided by N. N is moles of electricity transferred. The only way you can get N is to look at the correct net cell reaction equation. Times log of Q. So this is fancy reaction quotient Q. This isn't charge Q like we had over there. So please don't get them mixed up. So let's look at this system, since we've looked at this system previously. For this system, if I want to get E cell, do you remember what E0 cell is for this thing? You remember what standard cell notation is? Shorthand reference to many operating electrochemical cells is presented by standard cell notation. You did this in discussion. To express a cell in standard cell notation, you start by writing the formula for the anode material. If you're using an electrode that's not part of the chemistry of the system, you'd first write here the symbol for the electrode. Because you've noticed some of these half reactions, if they're going to be used as components of an electrochemical cell, have to be rigged with electrodes. What are electrodes? In the main, what's an electrode? What's an electrode? It's a current-carrying component of an electrochemical cell. But it may or may not be part of the chemistry of the cell. If I'm going to use the standard hydrogen electrode, so you see, we get funny words here again. What the hell does this electrode mean? Standard hydrogen electrode. Look at the standard hydrogen electrode in the notes. Hydrogen gas in the presence of water being oxidized to hydronium ion at pH 0, for which the assigned electrochemical potential value is 0. That's the standard hydrogen electrode, right? Well, I find it strange that this thing is called an electrode, because by itself this is hardly something that can be a component of an electrochemical cell. How am I going to connect another half cell to this standard hydrogen electrode? What would I hook my wire to? Hydrogen gas? I don't know how you can do that. Sometimes the words we use in science just kind of leave us cold. And this is one of the tough parts of this game, is to be successful in communicating the meaning of this stuff. So some electrodes have to be fitted with electrodes. Boy, that sounds like double talk, doesn't it? And this happens to be one of them, the standard hydrogen electrode. A very commonly used material is platinum because it's quite inert. What's inert mean? Not reactive. Carbon graphite, another material commonly used as an electrode. But let's not worry at this moment about electrode materials themselves. Let's worry more about the chemistry of the system. For this system, as zinc is oxidized to zinc ion, copper ion is reduced to copper, where copper in this case is the cathode. To run this, do I have to use copper metal as the cathode? Could I use silver metal as the cathode? Of course. What I need is a current carrier. And I have to use a current carrier which won't reduce copper ion, because this current carrier is in contact with copper ion, because it is on the surface of this current carrier where copper ion is turned into copper metal. So if I want to deposit copper metal on silver, I'll use silver as my cathode. I can use platinum as the cathode. But don't try using sodium as the cathode. You want to put sodium in contact with copper ion? If you put a large piece of sodium in contact with a large concentration of copper ion, you better get the hell out of the way. Because as soon as you put these things in contact with each other, whoom! And oh, my system just blew up. I didn't design it very well. Because sodium is a very potent reducer. And it isn't going to sit around and wait for zinc to do any reducing. It's going to murder copper ion on contact. Did you recognize that the stuff I'm talking about is all discussed in the notes which are attached to Table 2? Did you read the notes attached to Table 2? I hope so. All right, back to this. For this system, what's N? As zinc is oxidized to zinc ion, how many moles of electrons are transferred? 2. As copper ion is reduced to copper, how many moles of electrons are transferred? 2. And there's Q. Now then, for this reaction, could I write the equation 2 moles of zinc plus 2 moles of hydrated copper ion aimed at producing 2 moles of hydrated zinc ion and 2 moles of copper? Can I write that? Hey, it's my chalk. I'll write whatever the hell I want. Damn right I can write that. But if I write that, what's N? 2 moles zinc, 2 moles copper ion, making 2 moles zinc ion, 2 moles copper. What's N? 4. Right? The reaction equation always tells you what N is. Take a look at Table 2. And I'm going to give you a directive regarding tomorrow's quiz. If you couple half reaction 10, let's pick on half reaction 10. We're looking in the notes, not the information sheet, because half reactions are similar, but they're different numbered. If you couple half reaction 10 with half reaction 41. Half reaction 10 with half reaction 41. What's N? Ten with 41. 12. Because you got to multiply one of them by 3 and the other one by 4. That winds up giving you 12 moles of electricity being transferred. All right, back to this. Look at the table. Now, while you're looking at the table, let this Q term talk to you. What does the Q term say? It says that if I want E cell to be as large as possible, larger, for example, than E0 cell, in my Q term, how do I want the values for the components of the numerator to compare to the values of the components of the denominator? If I want E cell to be as large as possible, do I want zinc ion molarity to be bigger than copper ion molarity? Do I want copper ion molarity to be bigger than zinc ion molarity? Which one do I want large? Which one? This one? That's the product. Zinc plus copper ion making zinc ion plus copper. The biggest thermodynamic drive for that system will be provided when the copper ion molarity is huge and the zinc ion molarity is damn near nothing. Because the higher the zinc ion molarity, the greater the tendency to shove it in the opposite direction. Ain't that right, Le Chatelier? We don't want that. So let this thing talk to you. If you want E cell to be as big as possible, you want this numerator stuff to be as small as possible and the denominator stuff to be as big as possible. You see this minus sign? Because when this term is smaller than this term, you're getting the log of a negative number, aren't you? And the log of a negative number is plus or minus. Not negative number, but a number smaller than 1, pardon me. You get the log of a number smaller than 1. And the log of a number smaller than 1 is minus. So you get a minus times a minus. Ha ha! So arithmetically you get a boost to E0 cell, don't you? And E cell is bigger than E0 cell. Okay? Now then. You're in the lab. You're operating this cell. You have available 6 molar ammonia solution. I'm telling you, by using the 6 molar ammonia solution, can you do something to this system to make E0 cell and E cell both go up a whole lot? And if so, what's that something? Well, let's look at the possibilities. In the anode compartment, you have zinc being oxidized to zinc ion. Hydrated zinc ion. In the cathode compartment, you have hydrated copper ion being reduced to copper. Okay, so far? The standard notation for this cell tells us what I just said. So I can take my 6 molar ammonia and I can A, add it to both cells, B, add it only to the anode cell, half cell, C, add it only to the cathode half cell, or D, saying anything I do with ammonia makes E cell go down, so I won't do anything with ammonia. Those are the 4 possibilities. Only one of them can be right. Add my ammonia. Both half cells, neither half cell. Anode half cell only, cathode half cell only, which is correct? I'm listening.
The anode half cell.
Anode half cell only. Why is that correct? Are you looking at table 2? Because if I put ammonia in the anode half cell, is this going to be my oxidation product? No. Then the oxidation product is going to be this stuff. How does the stability of this stuff, the ammonia complex of zinc ion, how does the stability of the ammonia complex of zinc ion compare to the stability of the water complex of zinc ion? Look at the table. Which is much more stable? Because what this table is really is a storehouse of thermodynamic stability information. Table 2. Which is more stable? Zinc ammonia complex ion, zinc water complex ion. Zinc ammonia. So if I give zinc the opportunity to become oxidized and become zinc ammonia, wow, E cell and E0 cells going up big time. But if I make the mistake of putting ammonia in the cathode half cell, I'm going to take my copper ion aqueous, my hydrated copper ion, and I'm going to turn it into this stuff. And just like for zinc ammonia complex ion, copper ammonia complex ion is a lot more stable than copper water complex ion. The data in the table tell you this. So if I turn my oxidizer, which is hydrated copper ion, into the ammonia complex of copper ion, I now got something which is a hell of a lot more stable and therefore much more difficult to reduce than this stuff. So if I make this stuff, E cell and E0 cells coming down. And I don't want to do that. Enough. Go get them tomorrow.